we have finished the discussion on the equilibrium. So as I said, in the action notes set number 2, we have the main topic, and that is the rotational motion. And at the same time, there are 2 smaller topics which are kind of related to the mechanics, although they seem to be sort of isolated. But we have to really build on our understanding of the topics based on the knowledge of the linear mechanics and rotational mechanics. The first one is the static equilibrium. So we have gone through the concept of the static equilibrium. Basically, what we mean by the equilibrium is that you have the objects that are moving with a constant velocity and constant angular velocity relative to an observer. So that is the equilibrium in general. The objects could still be moving even if they are in equilibrium, just like what I've explained. A concept of the dynamic equilibrium is that you have the objects that are moving, but they are moving in opposite directions. So you have no net change in the situation. In particular, if all the velocities and angular velocities are equal to 0 and they are not changing, and this is the situation, we call that the static equilibrium. So this is the static equilibrium we are talking about in the lecture notes for chapter number 12. In the case of the static equilibrium, we have the objects that are not moving at all. Neither is it moving in the linear way or moving in a rotational way. So what we need is, according to the Newton's first law, in the linear form, there is no net force in any direction, and there is no net torque about any axis. If the objects are not moving to start with and there is no net force, it keeps at 0 velocities in all directions. Similarly, if the object is not rotating to start with, omega is 0 at t equals to 0, and the net torque is equal to 0, then our only conclusion is that omega has to be 0 at all times. That is the idea. So we are having these conditions, and all the analysis in the static equilibrium would rely on these conditions. So in particular, we are focusing ourselves to the situation where all the forces are within the plane and all the rotations are also within the plane. Or to be more exact, all the forces are inside the XY plane and the rotation is about the Z axis. So the rotation is still within the XY plane. So therefore, we have 3 resulting equations in order to satisfy the static equilibrium. They are force in the X direction equal to 0 and the force in the Y direction equal to 0. We haven't really decided where is X and where is Y axis. But the idea is once you define the X, you could immediately define the Y because they must be perpendicular to one another. Otherwise, the equations may not be satisfied. They may have components of forces that are neglected and they may disturb the static equilibrium. So when you write down the sum of forces at X equal to 0 and sum of forces in Y equal to 0, X and Y, we understood that they are perpendicular axes. And of course, the Z axis should be perpendicular to the XY plane. So the net torque about any axis Z, let us say it comes out of the plane, Z, any net torque about this axis Z has to be equal to 0. We have seen a couple of examples in the lecture notes by considering how the systems satisfy these three conditions, namely force in one direction equal to 0, and the force in the perpendicular direction in the plane also equal to 0. Finally, considering any point in the diagram, the rotation about that point, the net torque about that point has to be equal to 0 as well. So these are the conditions for static equilibrium. Well, please check the announcement for the contents of the midterm. So we have a couple of examples. In many problems, we have to be careful about the definition of the force direction and the force magnitude. The force direction is important because you might have components that sometimes appear and sometimes disappear. Say a rod in contact with a surface. It may be a pin contact, a pin connection. When you have a pin connection, it could provide a supporting force in the vertical direction. At the same time, the pin connection would be providing a normal force. Otherwise, the beam just push through the wall. So that is not possible. In that case, you have force components both in the X and Y direction. An alternative way to represent it is to have a resultant force R at an angle theta. Otherwise, if you have a wall that is smooth, like the example 12.3, then you would have only the normal force acting from the wall. Because the wall is smooth, it does not provide any frictional force. So you could see that in this diagram, no frictional force at the upper end, only normal force. And with that, you could still solve the problems. So that is the idea for lecture notes at chapter 12. Just for your information, we are having a midterm until chapter 11. Once again, that is announced in the announcement. So at here, we come to the last topic in the lecture note set number 2. This topic, in a certain sense, is kind of unrelated to what we have seen before. Of course, the concepts, some of them would be useful, and that is the Newton's second law, and also the rotational motion. So we have to delay the topic until now. On the other hand, knowledge or an understanding of this topic would be extremely important for any students who learn physics because of one thing. Many of the forces, many types of the forces in the nature, they would be arising from the interaction between two particles. No matter they are massive particles, charged particles, or even magnetic poles. Charged particles, for example, they experience forces that are acting on one another. If you learn it in the high school physics, you know the force depends on, of course, the type of charges. If they are positive poles, like poles, they would repel, unlike poles should attract. At the same time, the size of the force in this case should be inversely proportional to the square of the distance. So at here, we are, instead of talking charged particles, we are talking about massive particles. In here, we are not talking about electrostatic force. We are talking about gravitational force. And we have the similar equation such that the gravitational force is inversely proportional to the square of the distance between the two objects. If you like, that is what we are going to talk about. And if you are already satisfied, you could say goodbye to the lesson. But of course, I'm not hoping you to do that. We would be elaborating on the concept, of course. So at here, we would be describing the Newton's law of the what we call universal gravitation. It is universal, meaning that all objects in the universe, as long as they have mass, there would be gravitational forces between them. And we would try to establish the relation between the free fall acceleration, that is G, acceleration due to gravity, and the gravitational force. That is the agenda for this last chapter in the lecture note set number 2. Although the main message really is to introduce a very important concept in physics, the inverse square relation between the force and the distance, because that is what you're going to see later as well in the electrostatics. So all the things related to the gravitation starts from the actually observations in a very large scale, and that is the observation of the stars on, in the sky. Since the ages known to the human being, people have been spending a lot of time watching in the sky, probably because in the very ancient days in history, they have nothing to do. They have no mobile phones, and what they could do in the night is only watch the skies. And so from time to time, they have been collecting information about the location of particular stars or particular planets. And so a lot of the information have been gathered until the Middle Ages. They could basically describe what is the path of the stars, when they would come back, when they would be orbiting about certain areas in the sky with good accuracy. They know how long it takes. For example, they know how long it takes for the Earth to orbit around the sun, and they know how long it takes for the moon to orbit around the Earth. Just like the case of kinematics, they could describe the motion of the objects, but yet they do not know why. So in order to know why, here comes, once again, Newton. So the story is well known. He has been staying under the apple tree, and all of a sudden, the apple drops on his head. And the lesson from the story is that, according to the urban legend, the apple doesn't kill him. And then he starts wondering why the apple would fall down, but not other things hanging in the sky. For example, the moon. The moon is an object right above our head, and it is orbiting around the Earth. So if the moon is just like the apple, it should fall down. But apparently it doesn't. Well, at least up to now, it doesn't. It still stays very high in the sky. And yet, in order for the moon to orbit around the Earth, according to what we have just learned in the rotational motion, there must be a force. So I may have to redraw the diagram. There must be a force that pulls the moon towards the Earth. So where comes the force? And this force, according to Newton, it is just the same force that pulls the apple from the tree to the ground. But for the case of the apple, the force is pulling the apple to the ground because the apple does not have a tangential velocity. For the case of the moon, it doesn't fall down because there is a tangential velocity, and this tangential velocity helps the moon to keep moving together with the centripetal force provided by the gravity. So it seems that it is a reasonable explanation. You have the centripetal force provided by gravity, and the moon happens to have some tangential velocity. So happy ending, you have a circular motion. So with this special case of the moon orbiting around the Earth, Newton suggests that actually the gravitational force does not exist just between the Earth and the moon, or just between the Earth and the apple, or anything between the Earth and the surface of the Earth, but it is a universal phenomenon. It is universal in the sense that everything in the universe, there is a general attractive force between them. So that is the origin of the gravitational force. It exists because of the gravitational pull between two objects. So that is the idea of the gravitational force. And just to give a very quick summary on the equation form of the gravitational force, according to Newton, every particle in the universe, they would attract each other. Every pair of particles in the universe, they would attract each other. And the attractive force depends on the mass of individual particles, as well as the separation between the particles. So the actual relation, according to the Newton's law for universal gravitation, is that it is inversely proportional to the square of the distance. It is proportional to the square of the distance. So this is the equation form for the Newton's law of universal gravitation. G at here would be the proportionality constant, and that is called the universal gravitational constant. And with a specific value that, once again, I would not encourage you to remember. In any case, if they are needed, they will be given in the test or in the examination. But the equation form is important, naming that it depends on the separation between the particles as well as the specific property, which is the mass of individual particles that exist in this system. So we have the equation. The next thing the people have to do is, of course, to decide what is the value of G. Now, one could actually calculate the value of G For example, by making observations in the sky. In principle, you could also calculate the value of G, a large G, by checking the orbit of the moon, around the Earth. Now, one of the students asked a very good question. How is the R distance between the center of mass? We are so far talking about particle. Particles, by definition, have zero size. Later, we would expand the theory to large objects. But here, we first focus ourselves to particles. So it is not a bad question. It is actually a good question, important question. Here, we first focus on particles and assume the objects to be particles. So, okay, let's come back to what I've been talking about. We could make observations for the motion of objects in the sky and try to predict the path and determine the value of G. A great difficulty, of course, is what is the mass of those objects in the sky. According to the equation here, it's a bit difficult to know what is the mass of the moon or the mass of the Earth. So fitting in the equation may be a little bit tricky. So in order to have some good measurement, in many of the situations, we would like to determine the value of G in the laboratory. And that comes to the clever experiment by Cavendish in close to 1800. So the idea of the experiment is like this. If you have a pair of particles, or here he used 2 pairs of particles, it just doubles the force. These 2 pairs of the particles, of course, there would be attractive force between them. And if we have 1 pair of the particles that are very massive, we assume that they would not be moved when being held stationary. And the other pair of the particles are much lighter, so they could be moved due to the gravitational attractive force. And if they are really moving, let us try, according to Cavendish, let us try to hang the setup on a very thin piece of wire. And on that thin piece of wire, let us put a mirror. So if the small particles rotate, the wire would rotate as well, just like you are twisting a string. And this twisting of the string, of course, requires a torque. Kind of like you are extending a spring with a force. You need a force to extend the spring, and you need a torque to twist the string. And this torque, of course, is calculated by the attractive force times the distance. Is the attractive force, the gravitational force, times the moment arm, say the D. Just quick explanation without going into the details. Okay, the rotation depends on the amount of rotation depends on the torque, just like the amount of extension. The amount of extension depends on the force. The amount of rotation depends on the torque. And if the force is tiny, you expect the rotation will be very tiny. That is the whole story. So why we have to use the mirror here? It is actually a clever thing. You have a light source that is very far away. So If your rotation is only a small amount, then the mirror could help to cause the movement of the light beam by the same degree. And if your screen is far away from the mirror, then you will see the movement of the light beam. So by measuring the distance in which the light beam moves on the screen, he could actually calculate what is the rotation of the mirror. So that is actually quite a clever design. Rather than directly measuring the angle rotated by the mirror, he used a light source. He used a light source at here, and shine the light on the mirror, measure the movement of the reflected light beam during the rotation. So in this case, he knows theta. Once he knows theta, he would know the torque. And once he knows the torque, he would know the force. That is the whole idea. And let us try to put the whole thing into context. Suppose we are in the laboratory. Okay, let us try to erase all the things. And do a quick calculation. Let us assume these are heavy objects, 10 kilogram. This one, 10 kilogram as well. Just a quick estimation. So the gravitational force would be G times M1, M2 over R squared. Assuming that the spheres are initially separated by 1 cm, 0.01 meter, and M1 equals to M2 equals to 10 kg. Anyone who could do a quick calculation, what is the value? We are talking about gravitational force. So we are talking about the gravitational attraction between two objects in the universe. And of course, we are now trying to show you how tiny that force is by giving you some real numbers. Separation between the two objects being 1 centimeter, mass of the objects being 10 kilogram. If you put it into the equation, G, according to Cavendish, or according to modern day calculation, it is this value. You multiplied it. Okay, somebody has already calculated. 6.673 times 10 to the minus 5 Newton. 6.673 times 10 to the minus 5 Newton. So this would be the weight of an object that is 6.673 times 10 to the minus 6 kg, approximately. So you could understand how tiny that force is if you convert it into the corresponding mass. So it is not an easy experiment, even with the clever setup like this. But in any way, it provides you with some estimation of the size of the force, and therefore an estimation of the value of G. So this is the idea. The gravitational force would be calculated by the previous equation, and the law of gravitation tells you that for any pair of particles in the universe, there would exist such a gravitational attractive force. And the size of force is determined by the previous equation. Direction of force is that they would be pointing towards the center of mass or pointing towards each other. The particles have the attractive force that points towards each other. That is the attractive force. So that is why you have the, in the vector form, written in this way. Here, R12 correspond to the unit vector between the particle 1 and particle 2. And so it sounds quite counterintuitive, not close to common sense, but according to the physics, there would be attractive force between any pair of particles. It's just a matter of the size of the force. Typically, they are very small for objects in on this Earth, so you would not notice that at all. Okay, so now we come to the question that was asked previously. Not all the particles, not all the objects in the universe are particles. They are having sizes. They are having certain dimensions. So what happens to those situations? According to some calculations, which involve, once again, integration, as long as you have spherical distribution of densities, that means uniform densities in the form of spheres. That means symmetric mass distribution. And in particular, spherically symmetric. That means layers of the sphere that have the same density, if you like. So shaded regions in different color means different densities, but they are the same and in the spherical symmetric pattern. So if you have such a distribution of the mass, then when you use the Newton's law of universal gravitation, you could assume that all the mass of this object to be focused at the center of mass, And the Newton's law of universal gravitation is determined with the distance between the center of mass of the two objects. So we are having the similar equation form, but the meaning is very different. In the previous slide at here, we are talking about particles. Particles, by definition, have zero size. So the center of mass is just that particle location. So the distance r is well-defined location of the particle. But you would never, in the real situation, have particles. You would have objects of finite size with a distribution of the mass. As long as the distribution of the mass is spherically symmetric, as long as the mass distribution is symmetric in the form of a sphere, then you could assume all the mass to be focused at the center of mass. And Newton's law of universal gravitation takes the center of mass as where the location of the mass is, and use it for calculating the distance. So, for example, if you have a person standing on the surface of the Earth, then the Newton's law of universal gravitation would be calculated by considering the mass of the Earth, mass of the person, and the distance between the center of mass for the Earth and the person. That is the idea. And even with the same equation form, we are conceptually making a big jump from just particles to actual objects with mass distribution. Of course, where we consider the location of the center of mass of the person is of little significance, considering that the radius of the Earth is around 6,000 kilometers, and the size of a man at most is 2 meters tall. So it makes at most correction down to several places behind the decimal points, and that is a minimal change to the result. But conceptually, that is what has to be done. So we have the connection now between the gravitational attractive force and the acceleration due to gravity. Because, as we know, people are having weight, which is equal to m times g. And this, where does this weight come from? It actually comes from the gravitational attraction by the Earth on us. And according to what we have just seen, this gravitational attractive force, it is equal to g m over r d squared. Basically, you would be arguing it should actually be re plus h over 2, where h is the person's height and h over 2 is approximately where our center of mass is. Once again, this value, we are talking about 6 to the power 3 kilometers, 6 to the power 3 kilometers. So it's actually 6 to the power 6 meter. Here, we are talking about 1 meter. So correction is really small. And I do not see much difference between these two. So we just make it simple. So here, you have the equation. How do you compare the two? They are actually equal to one another. Therefore, G can actually be calculated in this way. GME over RE squared. Be careful that G at here is at the surface of the Earth. G at here is at the surface of the Earth. And G would vary according to location, because different locations have different distance from the center of mass of the Earth. And therefore, it could make a difference in the value of small g. Typically, at the sea level, it is 9.81, but it could actually vary according to the distance h above the Earth's surface. So if you are right at the Earth's surface, then mg would be equal to the Newton's law of a universal gravitation, and g is calculated from what we have just discussed. Small g equals to large G times me divided by RE squared. RE refers to the radius of Earth. If the object is at a location H above the Earth's surface, above the sea level, then R becomes RE plus H. So you have to change it accordingly. And of course, when R tends to infinity, the weight of the object appears zero, approaches zero. That is why we become weightless when you are in the outer space, because there is no further gravitational pull from other objects. Various locations above the sea level would give you different values of G. So if you are in the outer space, say in the space station, few thousand kilometers away, the value of G would be much smaller compared with that on the surface of Earth. And if you are really far away, then of course, G becomes zero. You would not be experiencing gravitational pull altogether. So if you look at the people traveling in the space station, the objects just stay in the space. When you are trying to eat, the dish will stay in the mid-air without falling onto the ground because there is no further gravitational pull. That is the idea. So at here, we just give you one example, I think, that is related to the one or two examples related to the calculation of the universal gravitation before we take a break. Here you have the space station at an altitude of 350 kilometers. That means apart from the RE, which is 6,300 kilometers, or 6.37 times 10 to the power 6 meter, you have the space station. Let us try to assume that it is a space station that is at an altitude of 350 kilometers, or 3.5 times 10 to the power 5 meter above the Earth's surface. So this is not a small value compared with the radius of the Earth. And plans for the final construction show the material of this weight measured at the Earth's surface would be lifted off. And you are asked to determine what is the weight of the space station when it is in orbit. So the idea is, on the Earth's surface, the weight of the material is this one. And you are asked to determine what is the weight of the same material, at the location 350 kilometers away from the surface of the Earth. So firstly, we decide what is the mass of these materials. Weight on the surface of the Earth divided by the G at the surface of the Earth. So you get mass. The mass is the same at every location in the universe. The weight, however, is different because value of G changes from the surface of the Earth to the location where the space station is. So the new value of G has to be calculated by this equation, putting in the H equals to 350 kilometers, and you would get the new value of the G at the space station. So you see this one would be the new weight of the material at the location of the space station. Slightly lighter compared with the material at the surface of the Earth. And then you're asked to decide what is the density of the Earth. Well, density, this is not some equation we would provide you in the examination, because we have to assume you have some knowledge in even the junior level science, and density is definitely something in a very junior level. So we have density, which is mass divided by volume. We assume you know, but just in case. Now, the mass is the mass, of course. Volume for the Earth, we assume that it is a sphere. So what is the equation for the volume of a sphere? This is something not provided, unfortunately, in the examination. Once again, we assume that these are the things you know, and we cannot really know what are the things you don't know. So we cannot provide all the equations in the examination. Just like we have to assume that you know what is sine squared theta plus cosine squared theta. Something like that. We assume that you know it is equal to 1. Otherwise, we cannot work at all. But unfortunately, that means we are assuming some standard equations that is understood or memorized by you, and they are not taught in this course. Of course, in a very junior level in the secondary school. So in any case, the mass of the Earth is this one, and that oh, okay, I put it as a mass of the Earth, mass of the Earth. So here we have the equation, which is also shown at here. Mass of the Earth divided by the volume of the Earth. The volume of the Earth is given here. Mass of the Earth kind of unknown, but we know that mass of the Earth is related to the small g and large g. At least on the surface of the Earth, small g is 9.8 or 9.81. Large g is the universal gravitation constant, which is calculated by the Cavendish experiment. Radius of the Earth, I assume that we know it is 6.37 times 10 to the minus 6. This can actually be measured by some astronomy techniques or by some geometric techniques. So that is obtainable. So in any case, all the parameters are known: small g, large g, and the radius of the Earth. So from that, you could calculate the density of the Earth. That is the idea. And it actually gives you some further clue of the composition of the Earth. Given that the density of the Earth is around 5,000 kg per meter cube, but the rock density, typical rock of granite, has only the density of 3 times 10 to the power 3 kilogram per meter cube. That means some mass is missing. That mass is coming from the center of the Earth, which is the iron core, as suggested by many of the scientists. So this is a great success of using the Newton's law of universal gravitation to predict even the composition of the Earth by some simple calculations. Now, how is this all these calculation of the gravity related to black holes that I showed at the very beginning of this lesson? The idea of the black hole is that it has a very strong gravitational pull. It has a very strong gravitational pull, such that the escape velocity would be larger than the speed of light. So in a scientific friction term of an explanation, not even light could escape. And of course, why can light be treated as a massive particles? That is something beyond our level. But the idea is you have a very massive objects in the universe that can have extremely large gravitational pull to the surrounding objects. So in order to have a very massive objects, you need to have extremely large densities. Idea is that you cannot have just normal materials, because in the normal materials you have atoms. If you study a little bit of chemistry, people will tell you that there is a nucleus and the electrons are flying around the nucleus. Well, of course, that is a very bad way of drawing a nucleus, drawing an atom, because the electrons are actually moving around in some kind of orbits, not anything like this. You have seen some better picture explanation of the atoms. But in any case, you have a lot of empty space in between. In the case of the black holes, probably you have just the nucleus part of the material focused at a very tiny space. So all the things are collapsed into a very tiny space. So the density is extremely high and it becomes very massive in a very small area. So that is why you cannot have the light, even the light cannot escape from those areas. This is, of course, just a very, very preliminary description. And students who are interested, please first go to the Nobel lectures or take a book of the brief history of time to take a look before you jump into the topic. But we will stop the discussion of the gravitational attraction at here. Okay. So we will take a break about 10 minutes, and then after the break, we would be moving on to the next set of the lecture notes, and that is related to waves. So we will take a break at here for 10 minutes. Okay, we should be coming back to the lesson. I guess many of the students are anxious to have a more and more practice questions, including the previous midterm papers. I would suggest you rather than focusing on working on just one particular set of questions, for example, just the test paper, just the exam paper, it is actually already useful if you have worked on the questions in the textbook. The idea really is to understand the concepts. So we are not having the test papers released for all the classes. So we do not have it at here. But instead, if you have any particular questions that you encounter in your working out some, for example, textbook questions and so on, you could always come and find us. Please, I have already listed the textbooks in the syllabus. And we have the free textbook, which is on the Blackboard. So you can make use of these facilities. So we will come back to the lesson. Here, we would be jumping to the next topic, next set of lecture notes that is concerned with yet another type of motion. But most of the time, it is regarded as a separate concept. The idea is that you have objects in the previous 6 weeks. We have been talking about the motion of the objects along a straight line or the motion of the objects along a circular path. Now, we will be coming to the third type of motion, a third important type of motion in objects, and that is the back and forth oscillations of the objects. And of course, when we talk about oscillations, we come into the idea of, say, waves. We come into the idea, say, oscillation motions. They are all related to one another. So that is the major idea for this set of lecture notes. We would not be talking all different types of waves. In fact, we would be talking about light waves in physics 2. There would be very detailed discussion of the reflection, interference, and diffraction in the physics 2. The lecture notes number 3 are just uploaded to Blackboard, I believe. I hope. So please check. Please check if the lecture notes are released for lecture notes number 3. Okay. Not sure what review you are talking about for lecture set number 2. Anyway, please drop the message and I'll try to answer it later. I should be focusing on the teaching for the time being. So at the beginning, we would be talking about different types of wave motion. Here would be just a quick summary on what you have learned probably in your high school with a little bit of extension. And afterwards, we would be making use of some concepts we have learned in the linear motion and combine them to the oscillation motion. There would be some mathematics involved, but after going through those mathematics, hopefully things would be easier. And in fact, all the things are something you have learned. So they are all built based on concepts we have learned before. And then we would be looking at a particular kind of what we call mechanical wave, and that is a sound wave. using the concept of sound wave, we would be going through an important principle called a superposition of the waves. This is a property unique among waves. When you have particles, that are hitting on one another, they bounce back. On the other hand, if you have waves hitting on one another, they would just go past each other. And during the meeting point, there would be something happening, and that is the superposition of the waves. After the meeting, they just gone past each other as if nothing has happened. But during the meeting, you have the superposition, and that leads to a lot of interesting phenomena. And those are the topics in the lecture set number 3. So at the very beginning, we would be talking about the waves in the most general sense. And in the lesson notes for the chapter 16 of the textbook, we would be giving you a quick revision on the description of a traveling wave. We would be here talking about waves moving from one place to the other. This is in contrast to the stationary wave, where you have what we call the resonance. At the beginning, we will be first talking about waves moving. And we would illustrate different factors that affect the speed of the wave in the string. And finally, just to give you some quick revision on what happens when the waves are meeting a surface. So you will expect the reflection of the waves and the transmission of the waves. So this would be a bit boring, so I try to finish them as quickly as possible. But for those who have not learned it in details before, they may be a good chance for a quick revision. There are many different types of waves, of course. You name it, water waves, sound waves, etc. But in terms of physics, there are specific ways. There are specific methods in which we try to categorize the waves. We try to put them into different categories according to different methods. For example, we could categorize the waves according to their medium of transmission. There are two major types. One is requiring a material as a medium. So that is something we call mechanical waves. So in this type of waves, you need to have a physical medium. Physical medium meaning some materials that is present. It may be useful materials, for example, a string, or it may be less useful material, well, such as air, which by itself is not a good material, but it is important because without air, you will die. So it still requires the material as the medium for the transmission. On the other hand, there is another kind of wave called electromagnetic waves, in which no material medium is required. Nevertheless, they can still be transmitted because they would be transmitted through the disturbance of the electric field and the magnetic field in the vacuum. So you have the electric and magnetic fields in the vacuum. That does not require the presence of any material. They would just be present in the space by themselves. So no medium required. And that is the electromagnetic wave. And in general, let us try to define what the wave is. The main idea for the wave is that, okay, you have seen the waves in the on the surface of the sea, particles are oscillating up and down. At the end, what the wave does is it does not just cause the oscillation of particles up and down, it is kind of the byproduct, if you like. At the end, when a wave is present, energy is transmitted. It is always the case. If you have a wave, you must have energy transmission from the source through the medium to the, if you like, receiver or the surrounding. Oh, sorry for very rough writing, but just a quick concept, so no need to write very clearly. Hopefully, it's just an introduction. So you have the energy from the source, and traveled or transferred over the medium, over a certain distance in the medium. In the process, particles in the medium or the electromagnetic wave does not have particles, but in the material wave, in the mechanical wave, you have particles. Those particles in the medium, they oscillate up and down. But after the wave has gone through, they are not moved from their original place. Material is not transferred. Say you have the particles on a string, and you just got the string oscillating up and down. After you finish oscillating the string up and down, it comes back to the original shape. Particles would not be all of a sudden focused at one end. It would still be in the shape of a string. Or in the case of the sea waves, particles are just oscillating up and down. During the process, energy is transmitted, but the particles, after the wave has gone through, it will remain in the original position. And mechanical waves requirement, you need to have a source for all types of waves. It depends on how you are generating the wave, but in any case, you need to cause some disturbance. You need to cause some disturbance to the medium before you generate a wave and before it can be transmitted. So this is one situation where you have a classification of waves according to the medium of transmission. The other way to categorize the waves is according to how the energy is transmitted and how the particles are moving in the medium. So this comes to the transverse wave and the longitudinal wave. The transverse wave is something shown at here. You have, say, a piece of string tied to a wall, and you hold on the other side. You hold the string on the other side. You move the string up and down. So the particles are moving up in this case, or maybe you move it down later, or maybe not. In that way, particles are moving up and down. Energy transmission, on the other hand, is in the direction perpendicular to the particle motion. So that is the idea of the transverse wave. Particles in the medium are moving in the direction perpendicular to the energy transmission. This is the transverse wave. So you could immediately recognize what is the difference with another type of wave, and that is the longitudinal wave. In the case of the longitudinal wave, you have the particles In equilibrium, they are stationary. Let us assume they are well and equally spaced. When you push and pull the spring, you would have some particles suddenly coming very close to one another, and some of them are getting very far away from each other. So here you see the particles are well separated because they are disturbed from their original equilibrium position. Particles are moving either left or right. At the same time, energy would be traveling towards the right. So energy travel direction is parallel to the particle movement direction. So that is the situation of the longitudinal wave. Where would you see a longitudinal wave? For example, you have a spring and you try to push and pull the spring. Standing wave does not necessarily mean longitudinal wave. I will show you some YouTube later and see standing transverse wave. So the idea is you have particles moving up and down, well, moving back and forth. For example, in the case of a spring, you have the elements moving back and forth, but the energy is also moving in the same direction. So that is the case of the longitudinal wave. So let me try if I can find something on the YouTube. Transverse wave. Transverse standing wave, maybe, on the string. Okay. So, well, this is an example. You can see that the wave is a transverse wave, but it is a stationary wave, especially when you can see the loops. We will talk about standing wave in chapter 18. So we would be talking about it later. Anyway. And in particular, we would be most interested in the waves that are periodic. A periodic wave does not necessarily mean it is a sinusoidal wave. A sinusoidal wave is just a special type of wave, which, of course, the shape of the wave can be represented by a sine or cosine curve. There are periodic waves which are not sinusoidal at all. For example, on the right-hand side, you could see the blue line, a square wave. You have sometimes that has the positive maximum, sometimes the negative maximum. These kind of waves appears a lot in the electronics. However, according to some mathematics, if you try to type in Google Fourier series, you will see that all kinds of periodic waves actually, all kinds of periodic waves actually can be represented as a sum of various sinusoidal waves. So it makes a very powerful tool called the Fourier series. All of the periodic waves can be considered as a sum of various sinusoidal waves of different frequencies and different magnitudes. For example, in the right-hand side, you will see that the blue wave is a square wave. And of course, it has, apart from the repetition, apart from the repeating distance, it has nothing similar to a sinusoidal wave. But hey, let us try to make it closer to a square wave by what? Adding a component. You see, we have added a component that has 4 times the frequency of the original sine wave. So yes, some of you have mentioned it is a harmonic. Typically, it is a harmonic that is added. In order to make it closer and closer to the square wave, you add in more and more harmonics. Of course, which harmonics to add, how large the harmonics to add, it is the trick of the mathematics. But in terms of the concept, we could do that. So when we study the wave, the most fundamental one would be a sinusoidal wave. Once we study the sinusoidal wave, all the things is just the addition of sine waves of different frequencies. That is the whole idea for the study of the sinusoidal wave. So that is why it is the simplest one. And of course, when we read the graph of a waveform, we have to extract some useful information, but it requires a lot of patience and caution. See at here what we have. It is a graph of X and Y. It means it is what we call a snapshot. What is a snapshot? You take a picture all of a sudden, and it is called a snapshot. It freezes everything in time. So this is just a picture. And here we have the particles that are frozen in time. So at a particular instance, you have the particles being disturbed from their original position. So the original position typically is regarded as y equals to 0. So I just try to highlight it a bit. So this is the equilibrium position. Particles, some of them are disturbed to the positive y. Some of them are disturbed to the negative y. Some of them are in between. And from this graph, we can determine 2 things concerned with the wave. First, it is what we call the wavelength. The wavelength is determined by the least distance in which the wave pattern repeats itself. In high school, you are told that the wavelength is the distance between the adjacent maximum point, which is a crest, or the adjacent minimum point, which is the trough. That is correct, because when you move from here to here, all the things repeat by itself, and that is the minimum distance for the wave to repeat itself. So that is the wavelength. But even if you move from here, let me try to erase all the things. Oh, sorry, erase all the things. Even if we try to move from here to here, it is still one wavelength, because when we move from here to here, all the things basically repeat by itself. And that is a minimum distance for the repetition. So that is the wavelength. A in this graph is corresponding to the amplitude of the oscillation. So typically we consider the amplitude to be a positive value. If it is a negative value, we just can put it back into the wave equation later. And apart from taking a snapshot, we can represent the graph by a plot of the displacement versus time for any particular location. So we do not have the simulation in the PDF, but if we can take a look in the PowerPoint file, this actually shows you a picture, or maybe I can just show you the PowerPoint file. If I could, let's try. Just 1 minute. Hopefully not spending a lot of time. Right, that is too fast, I'm afraid. But hopefully, what you can see here, hopefully, is that the particle is moving up and down. So it is, of course, varying with time. Therefore, we could try to map out the displacement of the particle from the equilibrium point as a function of time. At different time, the position of the particle from the original point would be different. So, I'm sorry, you cannot really stop it easily. So, at here, you have the displacement versus time graph. The position of the points on the graph correspond to the displacement of the particle at a certain time for a particular location in the wave transmission. So there are repetitions in this graph as well. The repetition is still a sinusoidal pattern. The minimum distance for the graph to repeat itself correspond to 1 period of oscillation. It corresponds to 1 period of oscillation, sorry. It corresponds to 1 period of oscillation. And once again, the value of A corresponds to the amplitude of the wave. That means the maximum displacement of particle from their equilibrium position. In the wave representation, apart from using the period, you could also use the term frequency. Period tells you how long the wave would take to repeat itself in terms of time. How long it takes in time for the wave to repeat itself. And that is the period. And the frequency tells you how many repeats would occur in 1 second for the wave. So they are, of course, related to one another. F is equal to 1 over T. T is the period, F is the frequency. T has the SI unit of second, and frequency has the SI unit of hertz. So that is something you should know already in high school. Let me try to share it once again on the PowerPoint, on the PDF. Okay, now we could kind of know that any wave pattern could be represented by a sine or cosine function. Let us just make the thing simple. Let us try to say they could be represented by a sine function first. So it would be always nice to represent all different kinds of waves using one general equation. This general equation is represented by the formula shown here. There are reasons why we get this equation. Basically, when you have a sine function, a normal sine function would be something like this. Wow, okay, it repeats forever and ever. It is theta, and this is the y. Y equals to, well, maybe a sine theta. Something you could easily understand. What is the amplitude? It is A. And what is this? What is this distance? If it is in terms of theta, you could easily understand this one should be equal to 2 pi. Because when you have sine theta and theta equals to 0, y is equal to 0. And when it is equal to 2 pi, it comes back to the original point and it is becoming 0 again. Of course, if you have the y versus t graph or y versus x graph, you would not have theta. You would not have theta. So we have to extend, contract, whatever, your graph from x to theta or from t to theta, such that when it repeats, in the case of the y versus t graph, in the case of a y versus t graph, it would repeat within time t, which is one period of oscillation. In the y versus theta graph, it repeats within 2 pi. And if it is y versus x graph, it repeats within lambda. So that is why we have the equation at here. You could see that the 2 pi comes in the front. If x is equal to lambda and t equals to 0, that could be treated as the snapshot graph 2 pages ago. That could be treated as a snapshot graph 2 pages ago. So if x is equal to lambda, the wave would repeat itself. So that explains why we have the x divided by lambda. And in a certain way, we could also understand why we put t, small t over large t. Small t corresponds to time, large t corresponds to the period. The only issue we might have at here is why we have the negative sign. In fact, you could have positive sign. The determination whether it is a positive or negative sign depends on whether your graph or whether your wave travels from the left to the right, that means along the positive x-axis, or travels from the right to the left, that means towards the negative x-axis. If it travels to the left, from the left to the right, y equals to a sine, I better write it again. If it is y equals to a sine 2 pi x minus lambda minus t over t, the wave is traveling in the positive x direction. Why is it? Why is it? For example, at the location x equals to 0 and t equals to 0, let us try to treat it like this. This is y, this is x. At the time equals to 0, we are seeing exactly this graph. So position of the particle is 0 at t equals to 0. So t equals to 0, y equals to 0. What about t equals to a little bit, say 0.1 second? Let us try to imagine what happens. After a short period of time, if the graph moves, if the sine wave moves from left to the right, it becomes like this. You see the particle moves downward. The particle moves downward. A slightly longer time from that, t equals to 0.2 seconds, it becomes like this. So you see the graph, the wave is moving from left to the right, but the particle at the position x is moving downward first before it comes back up and down. So if you draw the y versus t graph, at x equal to 0, what would you get? You get something like this. It is a minus sine theta graph. It is a minus sine theta graph, and that is why you have the minus sign at here for the wave traveling from left to the right. If you have the wave traveling from the right to the left, then it becomes a positive sign. So that is why you have the sign in the equation. So this one tells you direction of wave travel. If it's a negative, it is along positive x-axis. Sorry. If it is positive, that is along negative x direction. It is determined in this way. So this would be the general equation applicable for many different types of sinusoidal waves. Sorry, better not to highlight it. And there are some other ways of writing the notation, and people may combine, for example, 2 pi and lambda together, and it becomes what we call a wave number. And sometimes people would also combine 2 pi and t, and it may also be written as 2 pi f, and it becomes omega. We call it the angular frequency for omega and wave number for the k. So it becomes something like this. So this would be a mathematical way to represent a traveling wave. Here, A is the amplitude, maximum displacement from the equilibrium point. Lambda would be the wavelength. T would be the period of oscillation. So we understand it in this way. We are not talking about the relation of omega with the angular velocity. In fact, they are related, but we would not go into such details. When we talk about oscillation motion, we would, in many of the textbooks, you will see something called a phasor diagram. If you go to, for example, the university physics textbook, let me try to show it. you go to university physics textbook, I think you would have it. Oscillation, simple harmonic motion. Let me see if I can find the diagram. Yeah. So the oscillation in the simple harmonic motion would be kind of like the oscillation of the particles in the waves. And actually, you could represent the motion of the particle as if it is an object rotating in a circular path and having a particular component of the circular path being cast on the x-axis. So that is why it is actually related to rotational motion. I'm not saying that rotational motion, it is equal to oscillation motion. They are not the same thing, but they are something that could relate them to one another. And the angular frequency, which we see in the lecture notes, it is actually showing the connection between the rotational motion and the oscillation motion. When the object is oscillating, for example, and you could consider it to be the shadow of the vector, along the x-axis. So you could take a look later at at the chapter 15.3 in your university physics textbook, comparison between the simple harmonic motion and the circular motion. Yes, once again, your classmates have asked a very good question. Thank you for that. Okay, now, once again, we are getting a slight detour. And then let's come back to the lecture notes. Okay. Right, so I have been jumping a little bit fast. So you'll see all the things I actually talk about in your lecture slides. I just mentioned it a few slides beforehand. Wave traveling in the positive x direction, it is having the equation with the minus sign in the bracket. Traveling in negative x direction with the positive sign in the brackets. And the speed of the wave can be calculated by this equation, or f lambda. Why is it the case? You have the wave, for example, you have the wave, let us consider it in the y versus t graph. So it is at a particular location. It's in a particular location. So after a period t, it will come back to the same point. But over the period of time t, the wave would have traveled a distance of lambda. Over a time t, the wave would have traveled a distance of lambda. So the speed, which is equal to the distance over time, it is equal to lambda divided by t. Because after one oscillation, the wave For example, the 0 point of the wave would be moving over a distance that is equal to one wavelength. So that is why you would have this equation. And actually, the equation form at the top of the page does not cover all the situations. In the diagrams like this, like the one on the bottom left-hand corner, it starts always with starts always it starts always with y equals to 0 when x or t equals to 0. But in real situations, it would seldom happen. Sometimes you might have the wave actually starting at the maximum point or the negative maximum point. You might have the wave actually starting with the maximum point, so it drops like that. So the sine wave, the sine equation would no longer be valid. You may have to change it to a cosine equation, for example. But to be even more general, you could try to add in something called a phase. Now, this phase term is very powerful because this phase term allows you to adjust the wave to whatever point on the sine graph you like. If you do not need any adjustment, phi is just equal to 0. If you need to adjust it from the 0 point to the maximum point, you just make it equal to pi over 2, for example. Then when x equal to 0, t equals to 0, y is equal to a sine pi over 2, which is the maximum value. Then your graph would look something like this. So that is the idea of having the phase term. And this phase term should not change because it just helps you to adjust the initial condition. Right. I better stop it here. Just to give you a quick reminder, of course, we have the midterm next Monday, I remember. Okay. So the midterm is next Monday. It would be done on the Learn at PolyU. So please log in Learn at PolyU. When you log in, you would see something. You will see something on the content page. You will see something on the content page. Of course, the midterm at here just tell you the equation is, and there is a rehearsal. Now, this rehearsal doesn't contain the questions in the midterm, so give up if you try to take an early start. It just gives you some idea what is the midterm going to look like. You have some MCQ, you have some short questions. There are, I think, 6 MCQ and 7 short questions or something like that. You have only one attempt. There would only be one single attempt. Please note, you have only one single attempt. This is, after all, a midterm. So you do not have multiple attempts. And please remember, do not communicate by any means with anybody when having a midterm. Otherwise, please check the announcement for the number of questions. Otherwise, you would be very heavily punished. So please remember, you have to log in hopefully at 11:15 to make sure that you can log in completely. And the midterm should last for 50 minutes, 50. If you log in late, you would not have the extra time given back to you, because I have been told that you should start at the exact time of the lesson. So please log in before the lesson time, so you would have the full time of 50 minutes to complete the questions. It is exact time of the lesson, okay? All the instructions are the same with the assignment, so 3 significant figures should be fine. Right, if you have any other questions or any problems related to some tutorials or etc., please make use of the last chance of consultation tomorrow. So otherwise, I would be seeing you in Monday. Okay, so thank you very much.